Hello. Uh, yeah, good evening, everyone. I hope I am audible. Please confirm that anyone you can type on the chat box or you can open your mic.
Yes, sir, you are audible.
Okay, great. So I guess we can start now, or it's almost 6, so some of the participants might join later. So welcome everyone to the live session for the week 1 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving the similar assignment problems that has been given to you for this particular course for this particular semester. Uh, so, to be honest, this course is quite interesting with respect to if you are into some research domain or something, then this is a very important course to pursue certain research areas such as modeling. So this modeling has a very huge domain in terms of if I talk, let's say higher studies. So this modeling is very important with that perspective. Give me a moment. Yeah. So, like this is the course content. So the first week is very basic. I'll be giving some introduction on what is this nano electronics and what is this device scaling. And after that, we'll certainly move to some devices. We can talk about certain devices, but that will be covered like in detail in the further classes for this course that are basically FinFET's nanosheet. I hope you have some idea beforehand for this particular thing. And then the most like in terms of like numerical problems or the problems that have been given to you in the assignment, most of the problem will be related to this crystal structure, what is a unit cell, and some of the problems from Miller indices. So that will be covering in this particular week. And before starting all this, we'll be having some very brief introduction of what is basically semiconductor device modeling and simulation, and why is it basically important to go ahead. So maybe since this is a first class, so can you quickly uh, provide a short introduction of yourself? Maybe if you want, you can type in the chat box or you can open your mic and tell one by one. Let's have a very quick introduction since this is the first class, and I am hoping this class to be very interactive. And again, I'm telling this is a very important course if you are into this research domain. It will help you a lot. So actually, my PhD is also under this particular domain. So I'm doing this device modeling with the use of some machine learning techniques, which is quite trending nowadays. So I'll recommend that you should attend all the tutorial classes as much as possible. And yeah, we'll go along and we'll keep the sessions interactive. So I'll again request you can maybe type in the chat box or you can open your mic and tell a very short and quick introduction. Anyone up for it?
Oh, hi. Am I audible?
Yes, yes, you are audible.
Oh, hi, Anant and the team. I am Nilesh, and I am in semiconductor domain itself. I
Okay,
work at Global Foundries
okay, nice.
as an yield and integration engineer, and I have around 1.5 year of experience.
Okay,
And whatever work I do revolves around device. So I'm taking this course to expand my knowledge.
okay. So you want to work in the
Yeah,
modeling section, right? I do
yeah,
know a
like.
lot of people there. Maybe you can
Uh-huh.
contact me sometime. I know a lot of people in Global Foundry, so we can have a long chat regarding the same.
Oh, okay, nice.
Yeah,
We will surely
yeah,
have. Thank
sure.
you.
Yeah. Uh, yeah. Anyone else? I mean, whosoever wants to open their mic and talk, they can. Okay. Yes.
Hello, sir.
Yeah. So go
I'm
ahead.
Sania Manasre. Right now, I'm doing my graduation in
Okay.
electronics field, and I want to expand my knowledge as well as for the job purpose. I'm taking this course.
So you are a final year student.
Yeah.
You are doing BTech in AC, right?
No, actually, I'm doing Bachelor's of Science in Electronics right
Okay.
now,
Okay. BSc. Okay.
and I want to, yeah, and I want to pursue my career in VLSI.
Okay. Okay. That's great. Yeah. Thank you.
Thank you.
Hello. Hello, sir.
Yes.
Am I audible?
Yes.
Yeah, so my name is Arjun, and I'm also a final year BTech student. I'm currently at IP University Delhi.
Indraprasth.
Yes, sir.
Okay.
And
Yeah.
I also want to take this course to expand my skill set.
Nice.
Currently, I'm also working as a intern at under a professor under
Okay.
whom I am researching on thin film nanosheets and all
Okay. Nice. So on the fabrication aspect or the modeling aspect?
the modeling aspects.
Nice. Okay,
Yes, sir.
that's good. Okay, thank you. Next.
Yeah, hello sir.
Yeah,
Um,
hi.
Myself is Suresh, and just last July 2024, I completed my master degree from IIT Chennai.
Okay,
Uh,
IIT Madras.
yeah, yes, yes.
Nice.
Uh, and there, one of my professor, Tuhin, he is working in lab on chip. So I have done internship just only for 1 month. So I got interested. Basically, from I did my master from electronics and instrumentation. So I'm
Okay.
planning to pursue a PhD in lab and chip. So I,
What
I
did you say? Lab and chip.
yeah.
What is it? Is it some simulation software?
No, no, no. This is kind of MEMS for
Oh, MEMS. Okay. So
uh,
modeling aspect only you are trying to pursue.
modeling and as well as fabrication also involves for biomedical and biodiseases.
Okay, okay, I
So I
understood.
thought of this course might be useful. That is the reason just I registered and I want to explore this course.
Sure, that's great.
Yeah.
Yeah,
Thank you.
thank you. Anyone else who has left? Not sure. Bhuvan, did you give your introduction? Bhuvan. Okay.
Hello, sir.
Yeah. Hi.
Good evening, sir.
Yeah. Good evening.
I'm Bhuvan from Karnataka. I'm now pursuing masters in physics.
Okay. Nice.
I
From.
just want to explore the subject, and I was always concerned about electronics and these modeling aspect. That's why I'm here and
So
exploring this.
you are pursuing your masters from.
JSS University, Mysore.
Okay. Okay. Yeah. That's great. Thank you.
Thank you,
Uh,
sir.
Rikta, I guess you are left only. Rikta.
Hello.
Yeah.
Hello,
Hi.
sir. Hello.
Yes. Yes. You are audible.
My,
You can say.
yeah. My name is Rikta Kiran. I'm currently a student of third year engineering who is pursuing my BE. So I have a keen interest in this embedded system, VLSI, and
Okay.
signal processing. So I opted this subject. Thank you.
Okay. Yeah. Yeah. Thank you. So that's great. I mean, all of you have some background, and I'm assuming some knowledge for this particular course, and basically that will be helpful for you all also and for me also to give some basic introduction. So let me try to give you a very basic perspective that what is modeling. So I mean, does anyone already know what is modeling? I mean, not modeling, in fact, device modeling. Does anyone have any idea or anyone wants to try? Yes, who is this? Okay.
Hello, sir.
Yeah, yeah.
It is the way we are placing the transistors or the whatever components we are using to design the circuit,
Okay, you are saying placing the transistors is
or
something
the components we are using
component.
for our application.
Okay. Anyone else?
I mean, it's more about device modeling. So before forming a circuit, I mean, we have to do device modeling, so which will help us to design the particular circuit. Uh,
Sure.
I
Okay.
mean,
So you are saying it helps in
right.
designing circuit.
I mean, to design the specific transistor, so we have this particular GM, everything. To bring those parameters, if we do device modeling,
Okay, you
so
said.
we can tune it, and so that's why device modeling is required, as my perspective. But I'm not sure. I'm
What is
very
device modeling was the question. You're telling me what we can do using modeling, I guess. Yeah.
Okay, okay.
Yeah. So yeah, I mean that is fine. So that was a great response. Anyone else wants to try? Okay, so I mean, let me give you a very basic idea. What is modeling and why is modeling required? So you might have heard of fabricating certain chips, right? I mean, we have certain silicon wafers in which we do fabricate certain MOSFETs. I mean, if you have heard, so I'm hoping you are all are familiar with MOSFETs, diodes at least, right? That is very basic. I'm hoping that you already know what is a diode and a MOSFET. Is it the case?
Yes, sir.
Okay, yeah. So like we have certain silicon wafers like this, which are having a certain diameter, and we obtain or we do fabricate them by using certain fabrication techniques that I'll not go into. But so what is or why modeling is helpful is like if we want to fabricate, let's say a device which is let's say named X. So this modeling is nothing but the mathematical representation, or you can say mathematical equations that include certain, as he said, parameters. Give me one more thing, yeah. That includes certain parameters so that we can basically replicate the device behavior. I hope you know that this is a IV of a diode. Diode is nothing but if I write a equation which is I naught exponential of some V naught by eta Vt minus 1. This is a very basic equation, and diode is something like this, the exponential nature. So this equation is basically modeling, or implementing it is or giving it some mathematical representation is what is modeling called. uh, Guys, give me a moment. Hello, hello. Yes. Hello, hello. Oh yeah, sorry for the, am I audible, guys? Please quickly confirm if I'm audible.
Yes, sir.
Yeah. So
Yes.
what I was saying, that giving a mathematical representation or giving a certain representation so that a device behavior can be replicated is what is called as device modeling. There is one more term associated to it, which is also known as compact modeling. You have heard of it. This is a broad domain in the semiconductor industry, and like we have certain groups in India which are working on the compact modeling aspect, and we are also working on this particular aspect only. So yeah, so this is about what is modeling, and now why it is important is because let's say this is a device X that we have fabricated, but we have only, let's say we fabricated 100 devices on this particular wafer, but only 20 devices passed the test or they work. And so what we have lost is we lost a lot of resources, and 80% of the device were not working. So even before fabricating, what we can do is we can model these devices. Model means we can mathematically represent these devices and have some circuit simulations or some device simulation. Simulation is basically just simulating, I mean, basic word is simulating the device. And what we can do is we can capture the device behavior using the modeling, and using that we can save a lot of resources. So basically, we will be saving a lot of fabrication material. In fact, before going into fabrication, we do have a complete model so that it will replicate the behavior, such as if I talk in terms of MOSFET, so it can have modeling of different length of the gate, that is LG. Or if I talk in terms of diode, it can have different doping concentration, etc. So that is why modeling is very essential. Did you get the gist of it? Why, what is modeling and why it is important? Any questions right now? Uh, yeah, so that's great. So yeah, so in this particular course, we'll be talking about device modeling. So now, as I said, modeling is mathematical representation. So now, even if I talk about a MOSFET, let's say, which is looking something like this, let's say this is N plus N plus, this is source drain, and this is some oxide, and this is gate. So this, I mean, you must have read some drain equation which looks something like this. Let's say in saturation it is whole square. So do you guys know about this equation? Are you aware already?
Yes.
Yeah. Okay, that's great then. So like we have certain parameters, as it says, it is the mobility parameter, this is the oxide capacitance parameter, this is the width of the MOSFET, this is the length of the MOSFET. So once we fabricate a MOSFET, what happens is this particular W and L, they becomes constant. Let's say we have of this MOSFET, width is in the let's say Z direction, which is inside the paper. So this is nothing but width, this is the length of the gate, which is this L. This is VGS, which is the gate to source voltage. So what we can do is we can apply this certain voltage to get a certain amount of current out of it, which is the drain to source current. This there is a drift and diffusion happens, and there is a thing called channel formation. So once the channel forms, there is a certain amount of current that flows through it. So this is now a very basic model for a MOSFET, let's say. But as it says that what we are doing is we are going into nanoelectronics and device scaling. So this is one more important thing. So what does it mean is, sorry, yeah. So what it means is, let's say we have a MOSFET again of a certain length L. Again, the current is, let's say again mu and Cox W by L, something something. Yeah. So what is the basic objective of any semiconductor device? It is to have more and more current, right? This is the main objective of any semiconductor device. In your phones, we have devices which are trying to achieve more and more energy, or trying to reduce the power consumption that we have. So to have this current on a higher level, what we can do is we can either decrease the length. So by decreasing this denominator, what will happen that this current will increase. So this is what is called as Moore's law. I hope that you also know this, that every 18 months the transistor doubles on the same area. Let's say this is transistor doubles. So what happens is, like, we are keeping on decreasing this L. Let's say from here we went till here. So now there are certain regions, depletion regions, that could be formed, let's say around source or around drain, and that can already form the channel, and that will result in a lot of leakage current. That is some unnecessary effects. I mean, I'll cover them in detail in the further lectures, but let's say that even without the application of any voltage, these devices are giving a certain amount of current which is not desirable. So that is what I mean. This is, but first of all, this shortening the length or lessening the length is what is called as device scaling, because we want to have more and more current, so we are trying to scale it. But there are certain more devices such as FinFETs that is currently being used in every smartphone. So what we have achieved is, so I mean, some of you might have this iPhone 16. This has a 3 nanometer nanosheet, not nanosheet, I guess FinFET. So this is the lowest technology node that we have achieved till now. And let's say this is a FinFET. The channel length that I am talking about is in the node of 3 nanometer. So you understand 3 nanometer is so small that you know that an atomic radius. Do you have any idea what is the atomic radius of, let's say, any atom in a certain range, if you can tell? Anyone?
It's angstrom.
Yeah, it's certain angstrom, let's say 1 to 10 angstrom, and it is around a nanometer or something like that. So there are no even, let's say 3 nanometer if it is 10 angstrom, which is 1 nanometer. So there will be only 3 carriers in this particular channel, and what we want is we want thousands, or in fact 10 is per, let's say 16 per centimeter cube of the carriers in this particular channel. So by decreasing this channel length, we are dividing of these channel carriers. So this is how the device scaling has stopped a bit, and that is why people are more looking towards a more, let's say more materials that can help in uh, giving out the same current without reducing this channel length. So this is how new devices are coming into the picture. So first of all, this FinFET, then the recent, not the recent, but the upcoming technology is known as nanosheet FET. So we'll talk all of this in detail. I'm just giving you a very brief overview in this particular lecture, and this lecture might be a shorter one as compared to the other lectures that will be followed. So yeah, these are certain devices that are coming, and after that there is one more device that has come into the literature, that is complementary FETs, CFETs, that is what people are calling it. So the basic, like the summary out of it, like the length has so much shortened that we are looking for new materials, or we are looking for new ways to implement this, let's say this MOSFET, which is a very long, like it is coming out from a very long time. So in all the smartphone that we use contains FinFETs right now. So the basic objective was that this device scaling has also kind of stopped, and that is why we are looking at different nano devices and all, and modeling them. So as I said, MOSFET has certain equation. So if you go towards any compact model is again the file which has all the equations of the to capture the device behavior. So if I talk about any industry standard compact model, so one is, I mean, there is a group called BSIM group. So there is an industry standard compact model which is known as CMG. It has thousands of line, and in fact thousands of parameters. So it is very tough now to model, I mean, a certain CMG or a certain FinFET or a certain nanosheet. So this CMG can model FinFET and nanosheets, or basically in short, if I say gate all around devices, GAA FETs. So I hope you understand the complexity that I'm trying to bring out, that it is very tough to model any particular behavior in a device. So as you know that if I make a very simple IDVG, this is drain current and this is gate voltage, or a different IDVD. This is drain current and this is drain voltage. So I mean these has very standard basic equation which I wrote here. So very this is that equation. But if we go inside a certain complex devices, or in fact some different physical mechanisms, then they are very difficult to model. As I said that the current industry standard model has even thousands of parameter or thousands of equation. So yeah, so the basic thing is that is why the device scaling has kind of stopped, and people are looking for more different materials. So there is one material called as HFO2 that people are focusing a lot now. There are 2D materials that people are focusing a lot to have a certain power consumption, or to have a lesser power consumption. And that is why first of all the device scaling, so scaling it to in nanometer regime. That is why these devices are also called as nanoelectronics, or silicon based nanoelectronic devices. And device scaling, I have given you a very basic overview that decreasing the length, or uh, lowering down the length by a certain amount every year, or every based upon the time, is what we are calling as device scaling. So yeah, that was a very basic overview. I mean, this all will be covered later, but yeah, this is all about modeling and simulations. So
So
yes,
CMG is a I have a question. CMG is a software, is it?
no. CMG is a compact model. So I mean,
Compact model
yeah.
group.
So it has let's say thousands of lines of code. So one of the line would be something like IDS, as I said. It can also model this MOSFET. So let's say one of the line of that code is this. I'm talking on a very lower
Okay,
level, but it has thousands of line. I can show it to you
okay.
in the
Based
next.
on the condition, it will have a particular equation related to it, right?
Yes, yes. So for a FinFET, there will be a different current mechanism. For a nanosheet, there will be a different current mechanism. So based upon the device structure, it will have certain different equations. And there are various effects that come into the picture. So once you do this lens scaling, there is a thing called short channel effects. You might have heard of it. So because of that, there are certain effects that we need to model. So that all will be covered in the form of equations in this compact model. That is what we call as CMG. It is, I guess, multi-gate something. I'm forgetting the for C, but MG is multi-gate model. So multi-gate devices. So this all multi-gate FinFET nanosheet are multi-gate devices. Like this MOSFET has a single gate. This is the gate of the MOSFET. So FinFET has 3 gates, and nanosheet has all around like 4 gates for a single channel. So that is why this is called as multi-gate model. Understood?
Yeah, yeah.
Yeah.
I understand. I mean, FinFET has a three sides, right? Or three gate.
Yeah, it is. I mean, yeah, the channel.
Controlling.
Yes.
The,
So let's say this is a fin. It is wrapped around metal from 3 sides. This is what it
yeah,
is.
yeah,
Yeah.
yeah, yeah. You have control from the three sides, right?
Yes.
Yeah, yeah. Thank you, thank you.
Yeah. So yeah, I mean the basic thing is there is a lot to explore in this field. So that is why it is very good for research domain if you are looking for it. So let me quickly go to the very basics now, such as what is this crystal structure and what is Miller indices, and let me talk about a very basic thing, that is silicon, as all of the device is revolving around this particular material. So why is the case? So let's move to the first problem for the lecture. So it says the primary reason for the dominance of silicon in semiconductor device technologies. So like anyone who wants to give it a go, like they must be knowing about silicon at least. The yield engineer must be knowing about the silicon, if I'm not wrong. So any
I mean,
guesses?
yeah, you have the reasons already, right? I mean, the abundance of silicon on the surface.
Yeah, I mean there are a lot of reasons. So we
Yeah.
can, yeah. So the main reason is silicon is available everywhere. So the sand that we have in the nature is silicon. We can, I mean not silicon exactly, the we can extract silicon out of the sand that we have in the nature. The second thing is it is a very good semiconductor in terms of band gap properties. That is point B. I'll talk about band gap in the further lectures. That is a topic in I guess week 2 only. So what is a band gap and all? And then the main important or the most important property is this, the favorable properties of silicon dioxide. So what we have is, so let's say this is a silicon bar. So if we keep it in, let's say in room environment, what happens is due to the coming in presence of this oxygen, it forms silicon oxide on top, and this is a very good insulator. The second thing, if I talk about in terms of fabrication perspective, so we require this very smooth. The growing of this layer should be very uniform. I mean, there is should be no up and down anywhere once the silicon grows. So this is also very controllable for this particular material, that is silicon. So the most important reason, what you can say, is the favorable properties of this silicon dioxide, because it can be also used as an insulator. This is an insulator with a certain dielectric constant. I guess silicon dioxide has 3.9, and then silicon itself is a semiconductor. So a single material can be used as a semiconductor and as an insulator with some quantity in the oxide, and we can form a device. So that is why it is very important, or it is a very good material to have. And then it has a higher melting point, so this point is wrong. Silicon has a very high melting point if we talk in terms of uh, other semiconductors. So the primary reason would be the favorable properties for the silicon dioxide formation. So I'll see C is the correct answer for this particular problem. I hope this is clear. I mean, this is again a very theoretical point and some of the advantages of silicon that we have. Is there any doubts?
No.
Yeah, that's great. Okay. Anyone have any curiosity or any doubts regarding this modeling thing that we have discussed till now? I mean, everyone did get a grasp of what is modeling and why it is important, right? I mean, are you finding it interesting or not? That is what the main question is. Because in general, what we see is we have a very less participation, I guess. I mean, the lesser registrations in this particular course, because this is very device centric, or you need to have a particular focus on a certain aspect of semiconductor to score good or to have interest. So if you do find it interesting, please let me know. Like, is there anything that in particular that you have found interesting till now in this particular lecture? Anyone, if they want to say anything? Okay, so I'm assuming that some of the people might be finding it interesting. So yeah, so that is it. So let's move towards the further problem. I mean, this we can cover later because this will include a certain concept. Yeah, so let's cover this problem. So it says that consider a free electron moving with a velocity which is having a certain velocity which is 138 times of the speed of light. We need to find the de Broglie wavelength. Let's say I'm denoting it with lambda, the de Broglie wavelength, where c, the speed of light, is given as 3 × 10⁻meter per second. Then mass of the electron is also given. It is 9.11 10⁻31 kg. So anyone wants to say what is this de Broglie wavelength?
H upon P.
It's a
H upon P. Lambda equal to
lambda equals to what?
H upon P.
H upon P. Yeah, yeah. So I mean, this is de Broglie, but okay, fine. So let me cover the very basics for this particular problem so that we'll understand it better. So there are three basic phenomena that happen in any semiconductor physics device. One is photoelectric effect. That's the problem. First is photoelectric effect. The second thing is wave particles duality nature. And the third thing is uncertainty principle. You need to have the knowledge of these three things. Like, this is a very basic physics of that. So in order to understand this current voltage characteristic, we need to have some knowledge of electron behavior. So these three principles are based upon the electron behavior. So first is the photoelectric effect, as I said. So what is photoelectric effect? So it is given by, I guess you might be knowing, by Max Planck, and it indicated that, let's say we have a certain surface, and if we put some energy in terms of photons, let's say h nu is the energy. So there can be a injection or the removal of an electron from the surface, and it can convert this form of energy into light. So this is what was given by this Max Planck, and the energy was in terms of h nu, as I said, and this nu is nothing but hc by lambda. It's a very basic thing that if we put some energy onto a source, the energy will be quantized, and there will be energy quantas, that is the release of energy in terms of photons or in terms of light. So yeah, this is what we have. So if I can only say that when a light is incident on this surface, what we have, let's say this is a metal plate. The electrons in the metal can absorb energy from the light. So there is certain absorption of energy from the light, and electron can get excited, and they can receive enough energy so that they can get ejected from this metal plate, because this metal plate is full of electrons. I mean, metals are highly conducting, so they have a lot of electrons, and this phenomena is known as photoelectric effect. So I mean, is there any doubt in this particular thing, the photoelectric effect?
No, sir.
Okay, so if not, then we can move to the second thing, which was wave duality, wave particle, I mean. So what can happen is, this is an electron, it can also behave as a particle, it can also behave like a wave. This is what we call as dual nature or duality principle. So wave, by wave what we can say is, wave has a certain frequency, wave has a certain wavelength, wave etc. can be defined. And in terms of particle, what we can have, a particle can have a certain kinetic energy, a certain potential energy, etc. So electron can have all of that. So this wave particle duality is basically fundamental to the quantum processes that we have. And this is what is proposed by de Broglie, that we have a wave duality, and a certain particle can have a certain momentum, which is given by a wavelength, which is lambda is h upon mv, or h by p. So if I give you a very basic example, so let's say we have an electron, as the question suggested. I mean, let's say it has a charge of 1.6 10 to the power minus 19 joules. Sorry, charge, it is coulomb. Then let's say mass of the electron, it was 9.11 10 to the power minus 31 kg. And let's say the velocity of electron is something around 10 to the power 5 meter per second. So if I try to calculate the wavelength now, which is h by p, which is h by mv. So h is nothing but the Planck's constant, this is 6.63 10 to the power minus 34. Mass, I can write 9.11 10 to the power minus 31. And what is velocity? I have used 10 to the power 5. So the wavelength that will come out is around 7.28 10 to the power minus 9. So minus 9 is nanometer. So 7.28 nanometer. So what do you think? Is it a significant value to have, to consider it as a wave, right?
Yes, sir.
Yeah. So if I now quickly take, let's say, a tennis ball. Tennis ball, let's say, again the mass would be certain in grams. So let's say I'm writing 0.05 kg, let's say, which is around 50 gram. And let's say the velocity we can go up to is only 50 meter per second. Now try to calculate the wavelength. It will be 9 point, sorry, not 9 point, h by mv. So h is 6.626 and it's from minus 34, and we have 0.05 times 50. So that will come around in order of, I guess, minus 34 only. So this is 0.5 times 5, yeah, around in order of 34 only meter. So you see here, we can see that this mass can do a lot with wavelength. So we can conclude that large particles, these large particles cannot be treated like a wave, but these small particles having a certain very less mass and a higher velocity can be treated like a wave. So you understand now what is this de Broglie principle, or de Broglie wavelength, or the wave duality principle? Any doubts?
No, sir.
Okay, that is great. Then there is one more thing, which was uncertainty principle, which is proposed by Heisenberg. I'm giving very basics to you. I hope it is not boring. So the Heisenberg uncertainty principle, it states that momentum and position cannot be determined simultaneously for any at any time for any electron. So it indicates that there is no, at any point we cannot know the position as well as the momentum of an electron. We can either know the position, but we will not know about the momentum, or if we know about the momentum, we will not be able to judge the position of that. So that is why whole of the semiconductor physics revolves around this probability. You'll be seeing certain things called sorry, spelling I've written wrong. You'll see certain things such as Fermi function, etc., that will all be dependent upon a certain probability of finding an electron somewhere. So that is why this is the case. Give me a moment again. Vishek? Yeah. So yeah, that is the three main principles. So next, I guess there is a Bohr's model, but we'll talk about that later. Let's see what was the problem. So now we have a free electron moving with a certain velocity. We need to find the wavelength, and everything is given. So I guess maybe you can give it a try, and you can take 2 minutes and let me know what is the answer for this particular problem. I'll give you 2 minutes only. Uh, any answers? Did I get any comment? This is quite simple. Are you not able to understand or are you not able to solve it?
Doing the calculation.
Okay, yeah. Take your time, maybe 2 more minutes, and then I'll do the solve. So I've got an answer which is D. So let's check. So lambda is h upon mv. So v is 1 by 30 of c. So we can calculate v here. So 3 into 10 raised power 8 and by 30. So this will be 10 raised power 7. So h is 6.626 times 10 raised power minus 34 times 9.11 10 raised power minus 31 times 10 raised power 7. Okay, so this is minus 3 and this will be minus 10. So we can write 66.26.911 times 10 is per minus 10, not 10 but 11. So 9 7s is 63. So around 7 point something will be the answer, and 10 is per minus 11. Yeah, which is option D. So option D is the correct answer. Any doubts?
No, sir.
Okay, so then we can
Sir,
move.
here,
Yes,
sir,
yes.
here we are taking non-relativistic case, non-relativistic case. Can we
Yeah,
take relative?
so okay, so see, we are not talking about effective mass here, I guess, if this is what you are saying, because the question specifically said that the mass of electron is this. So we need to consider whatever the mass is given. If it was some effective mass, so it would have given a value of some x into m naught. So this m naught is a actual mass, which is this, and this x, which is around 0.01 or something like that, for the total effective mass. That will be the case for the relativistic case. This is the absolute mass of the electron.
Thank you.
Yeah. Fine, then we can move ahead. So what was I saying? Okay, so the next problem is, okay, so we have different, and yeah, so this will include the knowledge of now Bohr's model. That is the next topic. I mean, this is what we generally do in class 9 or class 11. So Bohr's model has, I hope everyone knows, it has three postulates. One, two, three. So the first postulate states that energy cannot be present everywhere. It is basically discrete. So what we can say that electron cannot occupy all the energy levels. Instead, electrons can only occupy states with certain discrete energy levels. And this is what the basic postulate one is. Then the second postulate is when a electron moves from, let's say, a stationary state corresponding to, let's say, some, this is a nucleus, let's say this is certain ground state, this is E1 state. So let's say when it moves from E1 to E0, from one stationary state corresponding to, let's say, some another stationary state, so the result is the emission of a certain energy which is given by this frequency. This is new frequency, which is E1 minus E0 by H. This is postulate 2. And the third postulate states that any stationary state is determined by the angular momentum of the electron. So there is a angular momentum associated with each electron. As I said that the electron is in discrete levels. So this angular momentum, which is mvr, is a integral multiple of nh upon 2 pi. This is postulate 3. So angular momentum of any electron is quantized and it is must be an integral multiple of h upon 2 pi. So these are the three Bohr's postulate. And if we have a certain, let's say, energy of electron, if we want to calculate, we can calculate with a very simple formula, which is nth electron has a certain energy which is minus 13 point, what was that, 56 z square by n square electron volt. And this electron volts means one electron volts has this 1.6 into 10 raised to minus 19 joules. And if I try to make it using a diagram, maybe, so this thing, if I try to make, let's say for z equals to 1, which is hydrogen, so we can have E1, we can calculate 1 by giving n as 1 and z as also 1. So it will come out to be minus 13.56 electron volt. E2 will come out to be certain value which is divided by 4, that is minus 3.39 electron volt. Then we have E3, which is more closer, which is minus 1.51 electron volt, and it can be up to infinity. Infinity is basically 0 electron volt. So this is energy with respect to the edge of the nucleus, and higher the energy level, higher will be the energy. So this is what we have for the Bohr's postulate, or basically the greater the distance of an electron from the nucleus, higher will be its total energy. Is it understood, all the three things? I mean, this is very basic class 9 stuff, so if you have any doubts, you can ask. Otherwise, we can move ahead.
Yes, sir.
We can move you.
Yeah, okay. So now the problem is, let E1 and E2 be the energy of an electron in the first and the second state of an hydrogen atom. So it is hydrogen. What is the value of E2 minus E1 in joule? So can anyone tell or wants to try it? Maybe you can take,
10 plus 2, 10.2, B option.
it is asking in joule. This is in electron
Oh,
volt.
okay. Wait.
Yeah, so let me write the formula to make it easy. This is minus 13.56 n square. I'm not writing z because it is hydrogen. This is electron volt. The question is asking in joule. So maybe you can take 2 minutes and type your answers in the chat box. I've got the answer quickly. A. So let's check. Let me also solve it. So it is asking for E2 minus E1. which will be basically E2 will be minus 13.56 by 2 square. Let me write it in electron volts itself. What was that? It is 3.39. Oh, sorry. There is a second term also, which is minus 13.56 by 1 square. It will be minus 3.39 plus 13.56 electron volts. And if I try to find it, it will be this thing minus this thing. So it is, I guess, 10 point something it will come, divided by, oh, not divided by, it should be multiplied by 1.6 times, that is 190. So it should be something 1.6, 10 raised to power minus, so 10 will give it minus 18 joules, which is any option. Oh yeah, option A is the correct answer. Is it clear to everyone? This is a very basic problem. Any doubts?
No, sir.
Okay, so I guess we can move ahead. I'll talk about more of the band formation theories in the next lectures, but there is one more topic, that is crystal structures and Miller indices, so we'll cover that. So now the problem states that we have a material X which is crystallizing as a diamond lattice. So we have certain different lattices. I hope this is already got. This is covered in the course, right? I mean in the classes BCC, FCC. What else? This is silicon lattice. There is, which is diamond lattice only. Is it covered in the classes? These things. I mean, then I'll only give an overview.
Yes, sir.
Okay.
Yes, yes, yes.
Okay. So FCC is nothing but face centered cube. BCC is body centered. So as the name suggests, let's say for the BCC, crystalline means we have, okay, I mean, I did not tell. So crystalline solid is that we have a periodic arrangement of cells. So this particular structure is in like periodic nature. So for, let's say for BCC, what we have atoms in all the corners. Let me make it complete. And face centered, that means every face has a half part of the atom. I mean every face has certain atoms. Or sorry, I was talking about body center. So at the center we have a atom, so that is why it is body centered. I hope this is clear. I mean this is straightforward. So now there is one more lattice, which is diamond lattice. So in the diamond lattice, this is the formation. So this particular picture, so we have atoms at all the corners, then we have atoms at all the faces, which is all the 6 faces, and then the third thing is we have 4 atoms which are present inside a unit cell. So if I try to calculate the number of atoms per cell, so it will be, so now if try to understand that this cube will be surrounded by all the other cubes. So can anyone tell how many cubes can be surrounded by the corners? Did you understand the question?
8 cubes.
Yeah, that is great. So one single cell will have only 1/8 contribution. Then we have phase. So again, this phase will be adjacent to some other phase. Let's say there is one more cube in this. Okay, sorry for the bad drawing. So this phase will be shared by how many cubes?
One more cube.
Yeah, one more cube. So there are total 2 cubes. So the
Two.
contribution of each cube will be half. So all the faces are 6. Then there are 4 present inside the atom for the diamond lattice. So it will be 1 plus 3 plus 4, that is 8. So number of atoms per cell for a diamond lattice is 8. I mean this is already good, but I'm just giving you a very basic gist. Then what was the question? Okay, we need to find the density of X. Okay. Then the mass of single atom. Let's say we want to calculate, because we have calculated the number of atoms. So it is nothing but, I mean this is a basic formula, that is atomic mass by Avogadro number, which is fixed. So this has a value of 6.023 to 10 raised power 23 grams. So now the density is nothing but atoms per unit cell times mass of an atom and divided by a cube. That is, I guess, given already. Is it given or not? Yeah, this is the lattice constant, that is a cube, that is already given. So this is the volume. That is why we are calling it density, and this is in per centimeter cube only. So that is why the unit will be gram per centimeter cube. So now we just need to put up the values. Do you want to try and solve it? When this is straightforward now.
A refers to bond length, right? Or is it different?
A refers to,
Lattice constant, is it
yes.
bond length or
What length?
bond length? Bond. So
Yeah,
distance between two.
yeah. So A is the distance between the two closest cells, or sorry, two
Okay,
closest
okay.
atoms. So it is different for different.
Sure.
So for the diamond lattice, it is equals to the radius of the atom. So A is R. So that is why we haven't changed this A cube. I mean, there
Mhm.
will be
Okay, got
certain
it.
changes for the FCC and BCC. So we'll do that in further questions.
Yep, thank you.
Yeah. So I mean, I can just write 8 times mass of one atom was this. Atomic mass is 30 for diamond. I guess I did not tell it, or it is given in the question by Avogadro number, which is 10 raised to 23 divided by A cube. A is zero point 0.6 nanometer. So I'm writing yes. Any doubts? Someone has
Oh,
opened.
no, 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 by mistake.
Oh, so it is zero point 0.7 times 10 raised to minus 7. I am writing because I need to put it in centimeter cube. So this is cube, I mean. So this will be the answer. You can try and solve it and let me know quickly what is the answer. I'm not sure.
18.4.
How much?
18.4.
Okay, yeah, this is an observation. Is it the same with everyone? Anyone getting some other answer, or is it fine? Okay, so this is minus 21. This is 10 is for 2 will be there. That will make it 10. 6 times 6.6023, and this is 8 times 3. 3 to the 4 by 6. I don't think it will be 18. 6. Oh, it is 0.3, 0.6 cube. So that will be 36,216. 0.216 will be only 2.16, and that is 2 ja. It should be around 1 only. Not sure. Anyone tried to calculate this with a calculator? I'm not getting 18, I'm getting 1 point something. I mean, that is also option, but I'm not sure. Can anyone tell quickly using calculator? Let me use it myself. So this 7021, then 100, then 10, 60 times 0.6 cube. 2.16 times 0.3, 13.009, 24 divided by 13.009. Yeah, I'm getting 1.84, something like that. Yeah. So the answer will is 1.84 gram per centimeter cube, which is option B. I hope this is the case with everyone and it is not 18. Right?
No, I got different answer, but maybe my calculation mistake. I got 0.18. This something I missed.
0.18. Maybe yeah, you can check later. That is not a problem. But the way I guess is a main thing. I hope you know how to do it now. Okay, so this is again one more concept which is Bragg's diffraction. So we might leave it. Let me do the similar questions first. So this is again this is a certain material with a BCC crystal structure. The density is given. The atomic mass is given. What is the atomic concentration? It is asking. Concentration means per centimeter cube only. The lattice parameter also it is asking. So we need to find the concentration as well as A as well as the atomic radius. So BCC has a certain different atomic radius. I hope you already know that. So atomic radius is calculated. I guess it is root 3 by 4a for BCC. You can check the lectures for the detail how it comes out to be root 3 by 4, but it is very straightforward. So you need to find A, R, and density. And yeah, there are many options. So maybe try to take 5 minutes and let me know the correct option. Is it fine with everyone? Or you want more time? Please confirm if it is fine with everyone.
Yeah, very fine.
Sure, sure. I've already got some answer, I guess. I did not see it. Option A. Okay, so let me try to solve it quickly. So it has a BCC. So for BCC, what we have is we have this structure. I mean, so 1/8. I mean, number of atoms per cell. Let me try to calculate again. So this is 8 in the corners, and plus what we have 1 in the body. So in total, we have number of atoms per unit cell is 2. Then mass of single atom again. So mass of single atom, it is nothing but atomic mass, which is 95.94 given, and 6.023 times 10 to the power 23. So I don't know what is this value, but we need to find the density, right? No, what we need to find? Oh, density is given, we need to find A. Okay, yeah, that is fine. So density is nothing but 2 times this thing, 95.94, and is for 23 divided by A cube. Now A is not given, but density is given. So this is equals to 10.22 gram per centimeter cube. So let's try to find A now. Again, we need to do a lot of calculation. So it is per cube. Has anyone done it?
3.147 into 10 to the power minus 10 meter.
A is
3.147 into 10 to the power minus 10 meter.
there are two options like that. So I'm assuming that he has calculated correctly. So it is 3.147 10 to the power minus 10 meter. So the second thing is very obvious now. So we can calculate the radius by root 3 by 4. This is 1.7. So almost half of that will be the R. I guess it is 1.3.
1.39.
So R we have this, A we have this. We have not calculated the concentration. So atomic concentration is nothing but this part. I mean, if we leave behind the mass, then I mean this is gram per centimeter cube. So if you leave behind this mass gram, so it will be per centimeter cube. So we can get 2 by A cube is the concentration. So 2 by what was the A? 3.147 and so minus 10 whole cube. So again, I mean, let's see the options. Okay, so only one of that has 1.36. So this is what n should come. So option A is the correct answer. Any doubts in this? Any doubts? Okay, I hope not. So that we can move forward. There's one more concept, which is the last concept, that is Miller indices. So we need to calculate the Miller indices for the following planes. So Miller indices is basically used to represent certain atoms or certain planes of a atom. So how we can do that? Let me tell you. So let's say we have a certain plane. So what we need to do? We need to check the plane first. We need to check the x, y, z coordinates of the plane. So once we check, we just write these in terms of A. In terms of A means whatever is the multiple of A, we just write them as the integer numbers. Then the step 2 is we invert the intercepts. Then step 3 is make it integer. You can multiply it with any integer so that this invert ratio is an integer. So whatever this integer is, let's say it is A, B, C. So this is the Miller indices of that particular plane. I hope this is already covered, right? I mean, is it fine the way that I have explained? Are you able to grasp it? Please let me know. If you are not, then I'll explain again.
Yes, sir.
Okay, then. So let's see for this example only. So you can see for the x coordinate, we have 2a. For y, we have a. For z, we have 2a. So what we'll write? We'll write initially 2, comma 1, comma 2. So this is in units of a. So this is step 1. Step 2 is inverted. So it will be 1 by 2, 1 and 1 by 2. So then we need to multiply it. The step 3 is multiply to get integer. So I guess the LCM is 2, so I'll multiply everything by 2, so it is 1 comma 2 comma 1. So this is nothing but the Miller indices. So first has 1 to 1. Oh, there are two options. So quickly give me the Miller indices of this. I mean, this is very easy now, I guess. So when there is no coordinate in the x plane, this means that this is going to infinite value. So for the x, we can take infinite.
Option
Yeah. So let me do it quickly. So infinity 1 1 will invert. So 1 by infinity will be 0. 0 1 1 is the inverted version, and it is already integer. So this is the correct answer. A is the correct answer. Yeah. So that was it, I guess. I have one more problem for diamond lattice, if I'm not wrong. Yeah. So this is again in this problem now the lattice constant is given, which is a Hart-Spare model. So this is nothing but diamond lattice only. Or not. Wait. Hart-Spare model is not diamond lattice. It is calculate the reduce. Okay. We have a certain ABC here. Let me check. So the distance between A and B will be, I guess, root 3A, right? Then the distance between A and C. A and C is where? Is it in the face? Okay. So A by root 2. I guess this is root 3 by 4A because of the centered nature. So A and B is 2R. No. This should be 2R. So R will be root 3 by 8A. Okay. Oh, A is already given. So yeah, so in this question we have a silicon. So we need to assume a Hart-Spare model. So we have these things. So in silicon we have a certain notation. So we need to find the distance between the point A and B, that is the maximum difference, and A and C, which is the minimum difference. So the minimum difference point is nothing but the radius of the atom. So in between A and B, the difference is if you try to calculate using the cubic method, from one corner of the cube to the adjacent, not the adjacent but the exact opposite corner, this things comes out to be root 3A. So this is the difference between AB, and the difference between AC, that is the corner from the face, this things comes out to be root 3 by 4A. And if you see very closely, I mean it is, I guess observable here. So this is R, I mean this radius, and there is one more R if you go till the center, if there is a face. So this is a diagram for BCC, but if it have been for FCC, there have been half R more. So this 2R is nothing but root 3A by 4. That is what I wrote there. Is it clear? This 2R is root 3 by 4A. Please let me know if this is clear.
Yes, sir.
Yeah, okay, fine. So A is already given. So we need to, the first part is we need to calculate the radius of the silicon atom. So R is root 3 by 8 times A. A is 5.43 and this is angstrom. So this is 1.176 angstrom if you calculate. Then the second is we need to find, what is the second part? Density. And C is density. Oh, sorry. Determine the silicon of density atom in atoms per centimeter cube. So this is basically concentration. So second part is concentration. So as I said in the last problem, give me a moment. Wait again. Hmm. Concentration is uh, so there is some effective number of atoms in one unit cell. Then there is this mass which is in grams, and there is a cube. So this is concentration. So again, it's a hard sphere model, so it is diamond cubic only. So diamond was 1 by 8 times 8 plus half into 6 and plus 4 inside. So this was, I guess, 8. Then a cube, we already know what is a. So concentration we can find quickly. This is 8 by a cube. A is what? 5.43. 5.43 10 square minus 10, not 10 but 8, because we want in centimeter cube. So 5 is 25, 125, 8 by approximately 125, 24. So do it 8, so we have 22, and it should be in order of 10 for 22. Oh, we don't have any options. Oh, so you can calculate exact number. It should be something, I guess, 125 into what is 0, 3, 4, 5 or 6. So it should be around 5 to 6 times 10
Yes,
raised by 22.
5,
Oh,
around 5.
it is 5. Okay, so let's write 5 to 10
Into
raised by
10
22 per centimeter cube.
gram atoms per centimeter.
Yeah, atoms per centimeter cube. That is fine. And the third is the density. So we have already calculated all the things. So I guess we just need to multiply it by the mass. Sorry. So density is this thing 6. क्या था? The effective mass of what is this? Silicon, right? The atomic mass is 28.09, 6.023 times 10 to the power 23 and times this concentration. So this is 10, 50. This should be 6, 4, 5, something 2 point. I'm not sure.
Yeah, 2.3.
2.3.
3.
2.33. Okay. So this is the density. I don't have any options, but yeah, these should be the answers. Is there any doubt in this?
No, sir.
Okay, that is great. So, I mean, these were some of the basic problems and the basic topics that I wanted to discuss for this particular week. And since this was an introductory week, so we can keep the lecture short. Uh, I can take some feedback like this is how you want to proceed with the tutorial classes, and what else we can do to make it more interesting or something like that. Anything from your side?
No, sir. It was great.
Yeah, thanks for the session.
Okay, then is there anything that any in particular anyone wants to say? Otherwise, we can dismiss for today. That is fine. We can meet next week.
Yes, sir. Definitely.
Yeah.
Yeah, thank you.
Okay, and one more thing that this will be shared regularly on the my YouTube channel. So let me write that also. I mean, you can mail me anytime if you have any doubts. So I'll provide the mail ID. This is the mail ID, and you can search this on YouTube. My name with NPTEL. You might get the YouTube channel also. So there are lectures for electronic devices and circuits also in this NPTEL channel, and also for digital electronics. So if you have interest in that also, you can check. But mainly now I'll be uploading the lectures for this modeling and simulations. So maybe kindly wait for a day for the YouTube video, or I will upload it by tonight only. I mean, just to give you the regular updates, this will be the YouTube channel. So I hope it is fine with everyone.
Okay,
Sir,
sir.
can you
Thank you.
ask some
Yeah.
question? Like,
Sorry.
are you, where are you doing, are you on campus like IIT Kharagpur?
No, no, no. I am in IIT Jodhpur. So I'm doing my PhD from IIT Jodhpur. So I'm a PMR scholar. So we need to do this NPTEL duty to have the fellowship. So I am a
Okay,
student at IIT Jodhpur, but I'm taking the TA for IIT Kharagpur.
okay.
Yeah,
Thank you, sir.
yeah. So yeah, it was great. So let's meet. I'm hoping that you all will join regularly because I don't want the attendance to be low in all the sessions. So please join regularly. And is this your YouTube channel? Yeah, you can search this thing and it will come up. I mean, something like that. This is not the YouTube channel, but yeah, there is a channel named Anant Singhal, but you need to write NPTEL to get it.
Sir, can you share this slides, what we have done, like all
Yeah,
this?
yeah. So this will be shared on the drive link that will be shared. I mean, that already been shared by the NPTEL team, I guess. So the
Oh,
slides will be shared regularly. I mean, I'll upload it by in 10 minutes after the lecture. So you should have that drive link from the NPTEL team so that you can access anything.
okay. Thank you, sir.
Yeah. So it was great. Let's meet next week at the same time. Yeah. So thank you everyone. Bye bye.
Bye.